All right, welcome. Sorry I'm a little late. Today is going to be all about quantum fidelity. So last time we talked about, trace distance. Right? So that's a one-shot distinguishability measure. We gave two interpretations of it. One in symmetric hypothesis testing, the other as absolute deviation between experimentally observed probability that could be observed from the state by doing measurements. Okay, so fidelity is an alternative measure commonly used. It has its own operational meaning, and there is a classical analog as well. Okay, so fidelity is a similarity measure. Okay. And let's start with its definition for pure states and then gradually increase the complexity to arbitrary states. And just to remind you, we need these measures for measuring the performance of communication protocols, right? And not only are these measures used in quantum information, but they're used in quantum computation as well, right? Standard metrics. In a quantum computer, there's an ideal gate or unitary evolution that you're trying to realize. And then experimentally you do something else. So these quantify the deviation. And trace distance obeys triangle inequality. So that's very nice for like calculating the total error as a sum of individual errors. Right? And it's used for it's called fault tolerant quantum computing's estimated threshold for fault tolerant quantum computing. Okay. So what you're learning here is useful beyond just quantum. Okay. So the pure states, we'll call them psi and phi. And then the usual thing we do is we abbreviate this as psi and phi. Okay. So we don't have to write it twice. So fidelity of the pure state density operators psi and phi we'll just define to be the squared overlap. Okay, and this is something that you learn in a standard quantum mechanics, right? This is the probability that if a system is prepared in the state phi, that it'll be measured to be in the state psi. So that's its operational interpretation. Okay, so let's make that a bit more formal, using things we've talked about in this class. So the fidelity is the probability that phi would pass the test for being psi. Right? So more specifically, what is the test? The test is a measurement, a binary measurement, binary outcome measurement, projection onto psi or identity minus psi. Okay. So if you get this outcome, it corresponds to yes, you passed the test. If you get this outcome, no, you did not pass the test. Right, and so this is a quantum mechanical test. This is how you ask quantum mechanical questions. Is the state psi or not? So let's calculate this acceptance probability. We know from the Born rule that it's going to be the trace of this measurement operator with this density operator, right? Trace of psi phi. And then when you calculate that, there's things that we've been using all throughout, you get the squared overlap, which is the fidelity. Okay? So that's a very nice interpretation. So you can imagine at the end of a quantum communication protocol, right? Let's draw like a diagram, the kind of thing that we'll be seeing a lot later on. So psi will be input, and there'll be some encoding, and there'll be a channel, and there'll be a decoding. Right, and technically we should probably wait a little bit to do this because the state of the output will be noisy, right? So this actually motivates the very next thing we're going to do. Okay, so let's just wait a second. Let's make a comment that the fidelity is symmetric. We can switch the arguments and it's the same. So that's a nice property. Okay, so now to generalize this formula, we'll do the next step. We'll make one of the, we'll do this scenario. So one of the states will be mixed, the other will be pure. Or one of the states will be general, it could be mixed or pure, and the other will be pure. So okay, so the generalization of the formula is this. It's exactly like this, except for phi you substituted rho. Trace psi rho, and then very nicely you can rewrite it as rho sandwiched by psi. It has precisely the same interpretation. The probability that rho would pass this test for being psi. So that's its meaning. And so now let's talk about this picture, right? So you should imagine that you're like a verifier assessing the performance of the protocol, right? So like this process happens, out comes a state rho, and then you want to measure, well, how close is rho to psi? Well, let's do a test to assess if the state is psi. So you do this test at the end of the protocol, and then the probability that it passes is the fidelity. All right, that's its meaning, and that's why we use it. In the literature, you'll see people define the fidelity without the square, but I very most emphatically like having the square so that you retain this meaning, right? The problem, this is like a physical thing you can measure. And same here. As far as I can tell, people eliminate the square for mathematical convenience. Because there are certain properties of the root fidelity that are nice. Okay? And we'll talk about that. But you know, there's this, I must have told the story before. There's this funny story about Max Born's paper on the interpretation of the wave function, where you know, he wrote the paper, and the original version, the Born rule, was written incorrectly. It did not have the square. And then in the final proof, before it went to publication, he put the square, and then that's what he got the Nobel Prize for. That's like, for good luck, we put the square also. Anyway, and then there's a generalization of the fidelity to its most general form that was proposed by someone named Uhlmann. And he put the square, and his paper is called "The Transition Probability in the State Space of a Star Algebra." Blah blah blah. It's published in a math journal. But his result is used all across quantum information and quantum computing, and we'll talk about that today. And the fact that the title of this paper says probability means put the square. Okay, so let's now think about how we would generalize this to mixed state or general states. So you could say, so I'm going to first write down something that I'll simply say is like the wrong definition. We're going to explore like why it's wrong. So after all this discussion, you say, oh, okay, we took phi, we substituted rho. Now let's substitute psi with sigma. Right? So and indeed, you could try to argue that this is somehow the probability that sigma would pass a test for being rho, right? So and what would the test be? Well, legitimately, you could say rho is itself a measurement operator, right? All its eigenvalues are between 0 and 1. So it's a legitimate measurement operator. In principle, you could realize this. And identity minus 1. That would be the outcome failed. So this is a bad definition. Why is that? Well, we haven't yet stated other desirable properties of fidelity, right? What are other desirable properties? If the states are the same, then the fidelity should be 1, right? That's like a basic thing. We'd want the probability that it pass a test for being itself to be 1, right? But that doesn't happen with this definition. And a number of you are nodding. I guess it's pretty obvious. So if rho is equal to sigma, then in general, trace of rho sigma equals trace of rho squared. Well, previously we saw this. This is a measure of purity, right? And in general, that's not equal to 1. You can get the lowest value by plugging in the maximum mixed state, right? You get 1 over d. So that's quite bad. As the dimension scales, the probability that the state would pass the test from itself, it's like 1 over d. That's approaching 0 as d gets large. So it's very, very bad definition. So we have to think about how to revise this, and this is the brilliant idea that Uhlmann came up with. Maybe I'll just erase this since it's a bad idea. All right. Okay, so Uhlmann's idea was to go back to the pure state formula and use the concept of purification, and that's what he called transition probability. Okay, so this is what we usually call Uhlmann fidelity, but it's really by now the standard definition of fidelity. Sometimes it's called Uhlmann-Jozsa, but it's not really fair. It's like Jozsa just like reinterpreted Uhlmann's results like 20 years later for the common person at quantum information. Because it was written in this like C-star algebraic language that many people don't. You just don't see that in like a basic course on quantum mechanics. So many people don't see that. So his idea was to optimize the pure state formula over all purification. Okay, so this is his definition. Fidelity of rho and sigma is the maximum called psi rho, psi sigma. These are purifications of rho and sigma. And that's the Uhlmann formula. Very simple to remember, right? You just take the pure state formula, optimize over purifications. And, you know, it has the desired property that we want. So, you know, if rho is equal to sigma, then there exists two purifications that are the same, right? And so the fidelity will be 1. And the opposite is true as well. If the fidelity is 1, the states are equal. So there's kind of faithfulness property as well. So if the fidelity is equal to 1, that means there exists two purifications for which the overlap is equal to 1. That means the purifications are the same, right? And then when you trace over the reference system, you'll get the same state as the definition of purification. So it follows that it's an if and only if. The fidelity is equal to 1, if and only if the states are the same. So let's just clarify, trace over R by rho. S. Now there's a system S with the specified because we have a purifying system of interest.
Practical to check.
To calculate this formula,
Right.
we're gonna talk about that. Yeah, there's a lot of interesting identities that come about. So to calculate it, there's a closed formula. We'll write that down. That does not involve an optimization. And furthermore, it can be calculated by a semidefinite program. This is what John Watrous discovered in like 2012, I think. Might have been 2009. He had 2 papers about semidefinite program. Okay. So let's explore your question. What do we know about purifications? We know that purifications are related by an isometry acting on the purifying system. If the purifying, I think we should make the discussion a bit simpler. If the purifying systems have the same size, then they're related by unit terms. Okay? That makes the discussion a bit simpler. So let's rewrite this formula. Let psi rho and psi sigma be fixed purifications. Rho and sigma. Okay? Then, and the reference system will be the same size as the system of interest. Okay. Then we get other purifications as this, like B rho R, psi rho RS, and B sigma or psi sigma RS. This formula we can rewrite like this. Instead of optimizing over the purifications, optimize over unit terms. So we'll optimize it over V rho, V sigma, psi rho, aggregate. That's going to be this this purification. And A sigma R sigma. Okay. Then what you do is bring them together. We just do some straightforward manipulations. V R rho, A sigma. Sorry, this should be dagger. Doesn't really matter. Then we get, if we multiply two unitaries, we get another unitary, right? So then we can rewrite this as maximization over unitaries acting on the reference system, psi rho rs u psi sigma. Okay. So that's perhaps a nicer formula. And now this we can use to prove what's usually called Uhlmann's theorem. Okay, so Uhlmann's theorem is the statement that the fidelity defined according to this formula is the same, is equal to this one. Okay. So that's the helps to address your question, right? So here you would take the density matrix. You have to diagonalize it, calculate the square root, right? For both, multiply them to compute the one norm. So that's all like linear algebra stuff, which is roughly like cubic in the dimension, as far as like a runtime for an algorithm. We do have a formula for Gaussian states. That's a solved problem because they overlap well. Okay. Using the definition of the trace norm, remember trace norm is this. We can identify root rho root sigma as A, right? And then overlap it with itself. And then this is a formula you often see in the literature, which when you first look at it, I remember when I was learning quantum information, I first looked at this formula, I was like, what is going on? There's so many square roots, right? But you know, once you get the hang of it, you're kind of used to it. So, okay. Let's prove Uhlmann's theorem. Might be able to do it in a few lines. Oh, the other comment I wanted to make is that often you see this introduced as the formula. That's the definition, right? But I would argue the progression that I presented to you is somehow more intuitive, right? Let's start from something simple, squared overlap, generalize that, and then this drops out as a consequence. Because otherwise, you first see this, and you're like, well, why is that? Why is that the definition? Okay, so to prove this, let's recall a fact from the mathematical preliminaries. I don't think we proved this, but you can prove it using singular value decomposition. Okay, so we're just going to state the fact. So for A, a square matrix, the trace norm can be calculated by the absolute value of A over all unitaries. Right? And the way that you prove this is it's like Cauchy-Schwarz for Hilbert-Schmidt norm. So you do that, you just something like that. And then you use the singular value decomposition of A to pick a suitable choice of U that saturates the upper bound you get from Cauchy-Schwarz, something like that. Actually, the bound might be using polar decomposition. I forget exactly, but it's in the book. It's a standard thing. Okay, so that we use, and then you know, A is going to be root rho root sigma, and then this U, I'm going to give you hints as the proof. It's going to turn out to be related to this. Okay. So good. So let's do it over here. So we start out with this fact about trace norm. and then we rewrite this as an optimization. Let's get rid of the square for now. Say already we get rid of the square for the mathematical calculation. Okay. So the next trick will be something from the mathematical preliminaries. The trace of an operator is equal to that operator sandwiched by the maximum entangled vector. Remember, the maximum entangled vector is this. Okay. So that's some fact you can prove. I believe Soria had that for homework. Is that right? I don't know. It's hard to remember who had what problem. And maybe you forget because you've done that calculation so many times.
Yeah.
All right. So okay, so let's use that. And take all this stuff and sandwich it by the maximum entangled vector. And now let's do system labels R and S. Identity on R, tensor, root rho, root sigma, U. Sorry, I kind of run out of room there. Maximum entangled vector. Absolutely not. Right. So we're just applying this identity here, and we get that. Okay. All right. From here, all this stuff acts on system S. So then we can use transpose trick. We put U on R. We put the transpose of U on R. Okay, let's do that. Max over U. Okay. And then now, in this formula, if we do a transpose of U, we're optimizing over all U. So we're going to reach all unitaries if we put a transpose or not, right? So the argument is that we can get rid of this since we're optimizing over all possible U. Okay, now we're actually pretty much done. So this root sigma can go on gamma RS. So let's rewrite it one more time. All right, identity on R, root sigma on S. Okay, root rho acting on S commutes with UR acting on a different system, right? So we can bring it over to the left. And now we have UR tensor identity on S. And then this right here is what we call canonical purification of sigma. And this is what we call canonical purification of rho. So we said that we could take these purifications to be arbitrary fixed purifications of rho and sigma. And then we get this formula, right? So that's the end of the proof. So these were, I'll just call these psi rho RS UR tensor identity sigma or that's the proof. And then square the whole thing, and then you get fidelity. So, you know, that's kind of a usual quantum information style calculation. You go to a purification, you do this kind of thing, you use transpose trick to move things around. And we'll be doing that kind of calculation again next week, very likely, when we go to entropies, relative entropies, and proving properties of them. Okay, so fidelity can be calculated by a semi-definite program. This I won't prove. It's in the book. It's just that I think you learn interesting mathematical tricks to go through the proof. So, but there's other things that I want to show about fidelity. So I'll just write down the SDP. And it is also for the root fidelity. The SDP has a nice form. So max over all linear operators, all right, L of H. So this is the set of all linear operators acting on the Hilbert space on which rho and sigma act. And what your objective function is the real part of the trace of X subject to this nice constraint rho sigma XX dagger in a block matrix. Right? That's a nice formula. As a reminder, the real part of trace X is the same as trace of X plus trace of X dagger over 2. Okay. That's the primal, and yeah, the proof is certainly not simple. Yeah, somehow you use a factor matrix analysis related to this positive semidefinite operator. I forget precisely what the factor is, because I didn't compare that one. Okay, the dual, if you calculate it, also has a nice form. It looks like expectation, the sum of expectations of observables. Okay, so you take minimize over positive semidefinite y and z. The objective function is what is the sum of expectations of observables, y rho plus trace z sigma. And this matrix has to be positive semidefinite. So that you can derive from the primal just kind of by the standard tools that we've used. So you rewrite the primal in the standard form that we presented, what might feel like ages ago. And then there's a corresponding to that, there's a standard form for the dual. You kind of simplify it and you get this. What is the use of this? Well, you could ask, like, why not just calculate it with this formula, right? In terms of a computational runtime, I think they would be comparable. Perhaps the SDP would be more expensive, right? So the answer is that this can be useful as an analytical tool, but I think the best use of it comes when we extend metrics for distinguishing states to metrics for distinguishing channels. Okay, because we haven't quite talked about that yet, but we're interested in measuring the difference between channels. And let me motivate that now. Why you'd be interested in that? So in a quantum communication protocol, the ideal process is to realize an identity channel, right? And then how do you try to approximate it? You do some encoding, you use the channel, you do some decoding, right? And then this whole process realizes a channel. And then we want to talk about the distinguishability of the ideal channel compared to the actual protocol that's realized. Right? And then to evaluate that, we want it to work for all possible states that you can input. And so trace distance, we would maximize the trace distance between these over all possible input states. Fidelity, that's because trace distance is a distinguishability measure. We want to look at the maximum difference between them. Fidelity is a similarity measure, so we do the opposite. We minimize the fidelity over all possible inputs. And then that involves an optimization over all possible input states, which you can combine with this minimization to get a semi-definite program to evaluate the channel fidelity. And then that's where I'd say this formula, this SDP realization is most useful. Because with the channel quantity, you have no choice but to optimize. Right? Okay. Properties of fidelity. Any questions so far? Maybe it's relatively straightforward. All right. Properties of fidelity. Well, let's see. Yeah, when we have this formula, you see that this is a state vector, this is a state vector, this is a unitary. So this absolute value is going to be between 0 and 1. Right? So fidelity is between 0 and 1. Fidelity equals 0 if and only if the states are orthogonal, perfectly distinguishable. You can also interpret it as least similar, since it's a similarity measure. Right? So what does orthogonal mean? Rho times sigma equals 0. Right? They're supported on orthogonal subspaces. That's what that means. And thus perfectly distinguishable by measurement. Okay, so why don't we prove this if and only if? And let's use this formula. Okay, so suppose that rho times sigma equals 0. Then you can take the trace of rho times sigma. That's going to be equal to 0. Right? You have, they're both positive semi-definite. So this you can rewrite as root sigma sandwiching rho. That's 0, right? These are just like, this at least is equivalent. These should be equivalent also, but I haven't proved that, so I won't write it. But this right here is a positive semi-definite operator. We took rho, we sandwiched it by root sigma. Right? So if the trace of that's equal to 0, that implies that root sigma sandwiching rho is 0. I don't know if there was a direct way to infer this from this, but this is what I came up with. Okay, and then this formula we also wrote it as that, right? So now if you plug in this is 0 to that, you get 0. So that's one way. Now suppose, let's do the other way. Suppose the fidelity of rho and sigma is equal to 0. Well, then what is that? That's equivalent to this quantity being 0. This right here is a norm. And what are the properties of norms? There is a faithfulness property for norms. The norm of an operator is equal to 0 if and only if that operator is 0. Right? So then this implies that root rho root sigma equals 0. And then this is identical to this. Or at least this implies that. Right? They are identical. But it's easy to see one implies the other. Left multiplied by root rho, right multiplied by root sigma. You get this. Right? And then they're supported on orthogonal subspaces. Okay. Now, what about the other extreme? Fidelity is equal to 1 if and only if rho equals sigma. Okay. So let's prove that. Yeah.
I mean, in this case, are all those double equivalences?
This should be, yeah.
And that is the proof, right? Both ways.
Oh, I see. Indeed.
I think you showed us in class that trace of rho sigma equal to 0 means rho sigma equal to 0 is positive similarity.
Oh, that's right. Yeah. Good. Okay, if rho equals sigma, let's suppose rho equals sigma. Then the fidelity formula collapses to just write everything for clarity. This way is very simple. Just collapses to the trace norm of rho. Rho is positive semi-definite. Its trace is 1. It's a quantum state. So fidelity is 1. Okay. The other way, there are several ways to arrive at it. At the beginning of the class, I told you one way. Yeah, suppose the fidelity, I'll just say it in words. Suppose the fidelity is 1. That means that this overlap is 1. That means there exists a unitary such that the overlap of this vector with this one is 1. But that implies that up to a phase that you can tune with the unitary, psi rho is equal to this vector if the overlap is 1. And so then you have these two purifications that are equal, and they're related by a unitary, right? And all purifications of a single state are related by a unitary in the reference system. So you trace over the reference system, you get the same state. That's one argument. Another argument is there are these inequalities relating trace distance and fidelity. We may or may not prove these the next time, but these are very nice inequalities that get used a lot. And here you see it pretty easily, like if fidelity is 1, then the upper bound on the trace distance is 0. The trace distance is always greater than 0. So then that both of those facts together imply that the trace distance is 0. And then using the property of a norm, rho minus sigma 0, rho equals sigma. So that's another way to see it. Okay. More properties of fidelity. It's invariant under isometries. what does that mean? If you apply the same isometry to rho and sigma, the fidelity does not change. Then you can easily prove from the definition. Let's do that. Let's start with the right-hand side. Square root of v rho, v dagger. Again, in the calculation, I'll just not write the square at the top. Okay. Square root of an operator, that's the square root of the eigenvalues, right? Under an isometry, the eigenvalues don't change, you just change the basis. So then that all implies that square root of v rho v dagger is equal to v square root of rho v dagger. Yep. So that you have, and that we'll use. And then once you have that, you basically done. V dagger of v, by definition of isometry, is identity. The norm itself is invariant under isometries in the very left and the very right. That was something we had argued in mathematical preliminaries. Let me get this and we're done. That's nice. You can also prove with Uhlmann's theorem with the overlap formula, and then you would see that v dagger would just cancel v. Okay. Fidelity, this is a nice property. We're often interested in quantum information, how measures, if you take tensor products, what they look like. And fidelity is a nice property that it's multiplicative. Okay. What does that mean? This to prove that, I think I'll skip this one. You just work with the definition. You work with this, have the square root acts on a tensor product of matrices, and use the fact that the one norm of the tensor product is the multiplication of the individual one norms. Okay. We said it's a similarity measure. How do we truly justify that with a data processing? Remember last time we said a distinguishability measure, it can only be called that if it obeys a data processing requirement. So a similarity measure, the measure should go up under a channel. So this is the data processing inequality fidelity. So the states under the action of a channel can only become of the same similarity or become more similar. Okay. Channel. Okay, to prove this, there are a variety. More similar. That's right. Yeah. Because the similarity measure. Remember, with the distinguishability measure, like trace distance, the interpretation is that they become less distinguishable. Fidelity is opposite of trace distance. That's the reason I call it short. So. If you want, you could this right here is a distinguishability measure. So its theta process inequality would follow the same direction as trace distance. All right. So let's prove it. So we'll recall the Stein-Spring theorem. Was that every channel can be realized by isometric evolution followed by a trace out of an environment. And omega equals trace over environment, e omega v dagger. I'm omitting subsystem labels. Why don't we write it for clarity? V is a shorthand for V going from S to V and E. S is the input of the channel. N is a shorthand for. Okay. So if you use the isometric invariance, fidelity of rho equals fidelity of V rho V dagger. And now, if we somehow had that fidelity does not decrease under the action of partial trace, then we could conclude the statement. Right? So I'm just going to write it, and then we'll prove that as the next step. All right, so if we, I'll write a question mark. If we have this, then we'll get the claim by Stein-Spring. I want to return to your point. So why should the fidelity be increasing under the action of the channel? Well, let's think of a simple, very simple channel. The simplest possible channel is throw away the input and replace with a fixed state. And then, like, under that, it becomes the same state. The fidelity is the largest possible guy, right? So that maybe helps a bit.
Yes, that helps.
Okay.
Initially,
Yeah, it's puzzling. I remember. Yeah. Yeah. It's like, usually, I think the reason it's confusing is usually you think fidelity being high is a good thing.
Right.
Right. And so, but that's usually with respect to like measuring the performance of a protocol.
I was trying to think about the second principle of thermodynamics.
Okay.
Exactly that. Having higher fidelity is having less information.
That's right. Yeah, you've made them more similar, lost distinction. Okay, good. So let's prove the question mark. Okay. So let rho AB and sigma AB the bipartite states. Okay. And what we'll prove is that fidelity of rho AB is less than fidelity of rho B. Okay, how will we do it? So we'll use Uhlmann's theorem again. That's going to be the main idea. All right. So let psi rho RAB and psi sigma RAB purifications. Rho AB and and sigma AB. Okay. So I think here's where a picture is very helpful, actually. This will be psi rho. And Uhlmann's theorem tells us that we can think of fidelity in terms of like a tensor diagram. So you have a U acting on R, and then we calculate an overlap with psi sigma RAB. Right? That's how we can like visualize the fidelity point. Or the whole diagram, you should put an absolute value. Okay. So that's how we can think about this left-hand side, right? And it's a maximization over all unitaries on the reference. So let's write that. If psi rho and psi sigma are purifications of rho AB and sigma AB, they are also purifications of rho B and sigma B. So what is the diagram for this? Well, for this fidelity formula, take two fixed purifications of rho B and sigma B, and that can be these same choices. We now optimize overall unitaries on the purifying system, which are, now it's a larger set of unitaries. So this set contains this set, right? And you're doing a maximization, so it really goes up. You have a larger set of which you're optimizing. That's the proof. Very nice with Uhlmann's theorem, right? So the way you can think about this is that with a larger set of unitaries acting in the purifying system, you can make the states more similar, right? And so it connects to the notion of fidelity being a similarity measure. That's the proof. So fidelity has data plus.
Tracing out the main statement, the inequality.
Yeah, so this is the inequality. Uhlmann's theorem allows us to act on the purified system of two purifications to make the states similar. The goal is to make one state look like the other, right? And so that's what you're doing here with this diagram that corresponds to this fidelity. These are the remaining systems that are, not the purifying systems. And then you can think that there's another party involved that's acting with the unitaries to make the states look similar, right? To make the purifications look similar, okay? To make the full global state look similar. And then if you have a larger set that you can use, see what remains with this person, with the person who's not optimizing, is fewer systems. You were there for Marguerite's general exam. We talked about verifier and prover. You can think of this person as like prover and these two as verifier. I don't know if that helps. Yeah. So yeah, Uhlmann's theorem allows you to think about things in terms of this globally pure state. And by leaving less to the parties involved, you're giving more power to the person who has the purification systems. And so there's a larger set of unitaries that you optimize. There's another way you can prove data processing using something that I think we'll possibly get to. Fidelity, there's a way to write fidelity as a minimization over classical fidelity of probability distributions that result from measurements. Why don't I just show that now? And we can think about it. It's a completely different way to think about it. Okay. So let's do this. Let's alternate method. So fidelity is also equal to the minimum of the classical fidelity. So this is an optimization over POVMs, generalized measurements. But before I do it, let me make one statement. So suppose that rho and sigma commute, then we can think of them as being like probability distributions, right? Because it's the same as having two states with probability distributions along the diagonal in some preferred basis, right? So like, so rho and sigma, let's suppose that rho and sigma are classical states that are just probability distributions, right? Then if you calculate the fidelity in this case, you can prove that it has this form. It's often called classical fidelity, or there's an Indian scientist named Bhattacharya. You can spell it like that. Is that right? Bhattacharya overlap. Okay, so that's classical fidelity. All right. So something that Chris Fuchs observed in his PhD thesis in 1995, I think, is that there's this nice formula for fidelity in terms of an optimization of the classical fidelity minimized over all measurements. Okay. So then, if you have this formula, remember the reasoning that we used to prove data processing for trace distance and the error probability and symmetric hypothesis testing. We said there, for the states rho and sigma, there's some optimal measurements. Right? And then if you do a channel first and then do a measurement, that's worse than trying to do a measurement first. The trace distance involved the maximization. Now we have a minimization. So things will go in the opposite direction. Right? So like, we can think of it in the same way that like, here's a box, rho or sigma. There's a measurement, using to distinguish them. But here, everything's opposites. It's a similarity measure, and you're minimizing. Okay? And so, you know, then if you first do a channel, and then measure you'll do worse, which in this case, the goal is to minimize, so they have a larger value of the measure. Right? So like this same reasoning implies that fidelity increases under the action of the channel. So that's another way to think about it. And then you can go through the proof of that. It's pretty similar to what we had for error probability and trace distance, but everything's in the opposite direction. All right. Since we're on this, why don't we prove this formula, fidelity via measurement? Okay, it's a very interesting formula, and yeah. Okay, so as a first step, we will use the fact that we have proved data processing for quantum channels, right? That we proved with this method, Uhlmann's theorem. Right? So we'll, let M be a measurement channel, M omega. This is a measurement channel, right? You measure according to POVM lambda x, store the outcome in the classical register with value x. And then this is the classical probability distribution or the density operator that results. So we can use data processing to say that this inequality holds. And then using what we just wrote here, we'll get this expression, right? So, from data processing, the inequality holds for all measurements. So since it holds for all measurements, we can minimize the classical fidelity over all measurements, and we get this inequality. So this implies that whole expression. All right, so we proved the inequality. Now, here's the interesting thing. To exhibit a choice of a measurement that achieves equality. And that's what I think I was very impressed by. This is something Chris Fuchs did in his PhD thesis. So he came up with an observable that is a quantum version of what's called likelihood ratio in the classical case. In the classical case, likelihood ratio is the ratio of P over Q, right? That's a classical concept. We said there are many ways to generalize a classical concept to the quantum domain. And here's one way that Fuchs came up with. This is what he called quantum likelihood ratio, or we can call it observable. So that might be a mouthful, but whatever. Okay, so we'll call it A, and it'll be this operator that's there in the fidelity itself, right? Sandwiched by sigma to the -1/2. Okay. So that's it's Hermitian, right? It's positive semi-definite operator sandwiched by positive semi-definite square root sandwiched by positive semi-definite. And so it's positive semi-definite, right? And one thing you can see is that we're just going to, so if sigma is not invertible, it's, this is the inverse on the support. That's the standard thing to do, right? For the purpose of this discussion, we'll just think that sigma is invertible. It makes it easier, okay? But then it's a full support state. So you have to argue, like you want things to work for pure states as well. So you have to argue how it works there, but we won't do that. It's in the book. Okay. So we said fidelity has this formula. And then if you use this observable, you can see that, well, it's the same as trace A sigma squared. So you can think of fidelity as the expectation of the A observable when the quantum likelihood ratio observable when the state is sigma, right? And then you see the cyclicity of trace sigma cancels when sigma to the minus 1/2 gives you identity. The things are invertible. Okay, so now we have to find a measurement that achieves this minimum. I'll just tell you what the measurement will be. It will be in the eigenbasis of this observable. Okay, so let's write down an eigendecomposition of A as lambda I psi I psi. So what does this mean? Well, if A acts on psi I, get lambda I psi I. Usual eigenvector thing. Okay. Now let's evaluate trace of A sigma. I think we need some space. Plug in the eigendecomposition of A. Basic steps. Okay. So that's basic. Now we're going to do something interesting. We're going to rewrite the scalar in an interesting way. So we said A is positive semi-definite. All the eigenvalues are non-negative. So we can, we can square and square root it. That's what's going on here. These are just scalars, right? And then we took this, we squared and square rooted. We get this and this. Good? All right. Now, use this. Substitute in A for lambda I psi. That's interesting. That's simple trick. We're actually almost done. And it's somehow, this is the non-obvious thing. This is equal to rho. Okay, why is that? Let's work that out. Claim is that this is equal to rho. So let's just work it out and the whole thing kind of collapses. Sigma minus 1/2, sigma 1/2, rho, half, half, sigma. So this whole thing was A, right? I'm going to mirror it over here. This whole thing is A as well, right? This part collapses to identity. This combines with this same operator, square root, square it, you get the operator at the side. So let's now write it. And now you see it, right? So pretty cool. And then that's it, right? We have row there. And we can do one more rewriting. Trace of psi I, well, trace of psi I sigma. And then you see that the measurement is in the eigenbasis of A. That's the measurement that's oh yeah. So just to trace everything that we did, we showed that fidelity is equal to trace of A sigma squared. Okay. Then there was equalities the whole way. Right? Trace of A sigma is given by this. So it's precisely the fidelity. And so that's an optimal measurement that achieves the fidelity. Right? Yes, but that was true for trace distance, right? In all these things, we assume knowledge of the two possibilities. It's not like you're going to have a universal measurement that can distinguish arbitrary state. Yeah. Go ahead.
So it's like we divide the expression of that trace itself by sigma and
This expression.
yeah.
You said it's like we did
Say
what?
multiply with sigma and divide the sigma. The divided sigma is like sigma minus 1 sigma.
Yeah. Yeah. I mean,
It's like it's true for like we can do this same trick for like positive sigma.
so I mean, positive semidefinite operators always have a square root, right? So we can do that. The way that this works in general is like if one state's pure or one's mixed, everything boils down to the support of the one that you're inverting. And so the support of this operator will be restricted to the support of sigma. And so you'll have the psi i's that are there in the support of sigma, and then the complement, but the complement won't matter for this argument. So that's kind of the basic idea of how it would go. But this is most interesting for like, I think when sigma has full support. Recent, we've been talking about bosonic Gaussian states throughout the course because that's the topic of interest. You can ask, what is this measurement for Gaussian states? So that was a question colleagues and I wanted to address, but weren't fast enough. Got scooped. But I think there's still more work to be done on that. There was a paper released by Leonardo Bonke, and I believe he had Korean co-authors. There's a group of like quantum information mathematical physicists in Seoul, Korea, who are interested in bosonic Gaussian states. So they collaborated and wrote a paper. But I found it a bit cryptic. Like, you want to know, like, what is the experimental procedure that you do to realize the measurement? So I think there's more interesting work to be done. Yeah. Oh, we are 4 minutes over time. You had a question, right?
Let m of
this line?
Yeah.
This was data processing. M is a
We're trying to
channel.
prove that.
Huh?
We are trying to prove data processing.
No. We proved data processing.
Using the other method?
We're using the other method, and we were now trying to prove this formula.
Oh,
And then I argued that if you have this formula, you get data
Then you
processing
get-
with another method.
I know this is
Yeah,
an
sorry.
argument way to prove data processing.
Sorry, yeah. It was, the goal was to prove this formula. Is that clear? Sorry, it's kind of like putting things together. Okay. Any other questions? If not, enjoy the rest of your week. See you Monday. I think we'll be getting into entropies and information on Monday. Yeah. Technically, there is no fall break because LSU canceled it, or Hurricane Ida canceled it. See you later, everyone.